Researchers use measurements to generate quantum entanglement and teleportation. Quantum mechanics is full of weird phenomena, but perhaps none as weird as the role measurement plays in the theory. Since a measurement tends to destroy the quantumness of a system, it seems to be the mysterious link between the quantum and classical world. And in a large system of quantum bits of information, known as qubits, the effect of measurements can induce dramatically new behavior, even driving the emergence of entirely new phases of quantum information. This happens when two competing effects come to a head: interactions and measurement. In a quantum system, when the qubits interact with one another, their information becomes shared non-locally in an entangled state. But if you measure the system, the entanglement is destroyed. The battle between measurement and interactions leads to two distinct phases: one where interactions dominate and entanglement is widespread, and one where measurements dominate and entanglement is suppressed. As reported in the journal Nature, researchers at Google Quantum AI and Stanford University have observed the crossover between these two regimes, known as a measurement-induced phase transition, in a system of up to 70 qubits. This is by far the largest system in which measurement-induced effects have been explored. The researchers also saw signatures of a novel form of quantum teleportation, in which an unknown quantum state is transferred from one set of qubits to another, that emerges as a result of these measurements. These studies could help inspire new techniques useful for quantum computing. One can visualize the entanglement in a system of qubits as an intricate web of connections. When we measure an entangled system, the impact it has on the web depends on the strength of the measurement. It could destroy the web completely, or it could snip and prune selected strands of the web, but leave others intact. To actually see this web of entanglement in an experiment is notoriously challenging. The web itself is invisible, so researchers can only infer its existence by seeing statistical correlations between the measurement outcomes of qubits. Many runs of the same experiment are needed to infer the pattern of the web. This and other challenges have plagued past experiments and limited the study of measurement-induced phase transitions to very small system sizes. To address these challenges, the researchers used a few experimental sleights of hand. First, they rearranged the order of operations so that all the measurements could be made at the end of the experiment, rather than interleaved throughout, thus reducing the complexity of the experiment. Second, they developed a new way to measure certain features of the web with a single probe qubit. Thank you for watch. Please subscribe, like and hit the bell icon.